Hello students, in today's class we are going to see about the ARM and thumb instruction set. So ARM processor handling 32-bit ARM instruction set as well as the 16-bit thumb instruction set. So here how the ARM and thumb program counter getting incremented when it's processing the instruction. So here normally the ARM use fetch, decode and execute cycle to execute the instruction, and when the ARM is fetching the instruction, the program counter it's incremented by 4 during the decode cycle, and during the execution cycle it is incremented by 8. During the thumb instruction, how the program counter varies. That's what shown in the figure. So there are 3 types of ARM instruction. One is the data processing instruction, then data transfer instruction and control flow instruction. So here the data processing instruction in between the registers, and data transfer instruction between the registers and memory, and control flow instruction only change the value of program counter and it will not vary any value in register or memory. So first let us see the data processing instruction. Here all the operands are 32-bit in size. So it may be a register or immediate value. The result, if any, is also 32-bit in size and it goes to a specified register. So only one exception, that is long multiply. It generates 64-bit results. All operand and result registers are independently specified as a part of the instruction. So first let us see the arithmetic instruction under the data processing instruction. Here arithmetic instructions are add with carry, subtract with carry, reverse subtract with carry. So here R0 is the destination register and R1, R2 are the source register. So the content of R1, R2 are added and it is stored in R0. Similarly, addition with carry. Then subtract. So here the destination register is R0. So R1 minus R2 will happen. The content of R1 minus R2 will happen and the result is stored in R0. So when we are using the reverse subtract, so whenever we need to change the source register, in some application we need to reverse this source register. So instead of doing R1 minus R2, we have to perform R2 minus R1 for the shifting operation. So for that application we are using the reverse subtract. Similarly, reverse subtract with carry. Here all the operations can be viewed as either unsigned or 2's complements. So next is bitwise logical instruction. So here the bitwise AND or XOR and bit clear operation has been done and the results are stored in R0 register. So BIC is the bit clear instruction. So next register to register move instruction. So here we have seen move as well as move negated. So here the R2 content of R2 register moved to R0. Here the content of R2 is getting noted and it is moved to R0. That is the difference between move and move negated. So the next one is comparison instruction. So in this instruction, any register value or memory value is not affected. Only the current program status registers condition codes, that is negative flag, zero flag, carry flag and overflow flag are affected. So here the source register is compared with destination register. So for comparing R1, R2, it will perform subtraction of R1 minus R2. Depends on the result, it will affect the conditional codes. Similarly, for compare negated, it will perform R2 minus, sorry, R1 minus of R2. So minus of minus of R2 will become plus R2. So based on R1 plus R2 result, it will affect the conditional codes. So for the test R1 comma R2, it will perform R1 and with R2. So based on the test result, so it will affect conditional codes. Similarly for test equal, these instructions do not produce result in any register. Specifying immediate operands. So here the immediate value has been specified by means of the hash. So hash 2 represent the immediate value of 2. So that value is added with the content of R2 register and this value is stored in R1. Similarly for sub and AND instruction. So here hash represent the immediate value in this and ampersand represent the hexadecimal notation of this value. The next one is shifted register operands. The second source operand may be shifted either by a constant number of bit position or by a register specified number of bit position. So for example, in this example, they have given LSL. So first we will see what is LSL. LSL is logical shift left, then logical shift right, then rotate right extended by 1 bit, then arithmetic shift left, arithmetic shift right. So here in this example, they have given add R1, R2, R3 LSL hash 3, which means that the R3 bit position is shifted towards left by 3 bit position and the result is added with the content of R2. So this result is stored in R1 register. Similarly here, how many bits should be shifted, that has been mentioned in R5 register. So based on the content of R5 register, the R3 register contents are shifted. Then this value is added with R2. This two results R2, then the final result of R3 is added with R2 and this is stored in R1. So this is the difference between the arithmetic shift and logical shift left. So if they are mentioning logical shift left by hash 5 means it will shift the bits towards left by 5 bit position and the empty space it will fill 0 value. Similarly for shift right, it will shift towards right 5 bits and the empty space it will fill 0 value. But in the case of arithmetic shift right, so again it will again shift the same thing. For 5 bits it will shift towards right, but the empty value will be filled with MSB bit position. So whatever thing, either 0 or 1 in the MSB, that has been filled in all the fields of the empty. Similarly here, for the arithmetic shift right, instead of 0 there is a 1 in MSB position. So after shifting, the empty places has been shifted with 1. So you know that how many rotate right. So for that rotate right, bits are shifted towards right and the empty places again filled with the shifted one. So that is rotate right. Then the multiplication instruction. Here the multiplication instruction will multiply R2, content of R2 and R3 and the result has been stored in R1. Similarly multiply accumulate. So in this register, then R2, R3 is multiplied, that result is added with R4, the final result is stored in R1. That is the multiply accumulate. Then the data transfer instruction. So the ARM instruction set supports 3 types of data transfers. One is single register load and store, multiple register load and store, and single register memory swap. So let us see what is single register load and store. So always all ARM data transfer instruction uses register indirect addressing mode. So what is that register indirect addressing mode? So here they are given address R1 comma table. So in that value, the table value holds the memory address that has been stored to the R1 register. Okay. So here they have given the example, that is load register. Load register, that means load to the register. Then it is STR. STR stands for stores from register. So loads to the register, which means that the content of R1 which is loaded to the R0. So what is the content of R1? It is the address. So in that address there will be some value. That value is moved to the R0 register. So always for the load register, the data transfer will happen from the right to left for all the instruction, but for store instruction alone the data transfer will happen from the left to right. So here the R0 value is stored to the content of R1. So the content of R1 holds some memory address. In that address this value is moved. Then single register loads and stores. So this is the example we have already seen, that LDR and STR. So an alternative form uses register indirect with offset, which means that they have mentioned R0 R1 comma #4. So which means that this R1 value, that memory value added with 4. So the address value increased to 4. In that particular address, what is the content? That content is moved to the R0. So the similar thing happened here. So the R0 content is moved to the this value. So this register address. So what is this register address? That is the value of R1 plus 12. So R1 holding some address value that is added with 12. In that address, if the R0 value is moved. So this is about single register loads and then can go for the byte and offer to be transferred. So here the LDRB represents load register byte. Then STRB stands for store register byte. Then this LDRSS store meant for load register half word. Similarly, store register half word. So the transfer between R1 R0 will happen in the same way how we have seen the LDR and STR. So this is the multiple register loads and store. So LDMIA stands for load multiply increment after. So LDMIB represent load multiply increment before. So here what will happen? So the transfer will happen from left to right. So the content of R1 is stored to R3. Then the content of R1 is incremented by 4. Then it is stored in R5. Then the content of R1 is incremented by 8. Then this content is stored in R6. Similarly for LDMIB. So the list of destination register may contain any or all of R0 to R50. So the supported with the addresses that can increment or decrement before or after each transfer. So then the ARM does not support any hardware stack. Then software stack can be implemented using the LDM and STM family of instruction, load memory and store memory. Then we will move on to the control flow instruction. So here the control flow instruction got the 4 types of control flow instruction. One is the unconditional, then conditional branch, then branch and link, then conditional execute. So we all know that based on the condition the branch will happen. So here without any condition, the control will move on to some target. Okay, here based on the condition of branch not equal. Based on this condition, the control will move on to the. So these are the some of the branch instruction we are using in the ARM processor. So this is the branch and link instruction. Then the conditional execution instruction. Based on the condition, the control will move on to another loop. So this is the post-week and sacral. So this is about ARM instruction set. Thank you.